Okay, everyone, welcome back. So it's about the time to start the second session for this morning. So we are honored to have Professor Jun-cheng Wei from the University of British Columbia and the Chinese University of Hong Kong to give us a talk about the stability of Sobolev inequality. Professor Wei.
Okay. Okay. First of all, thank the organizer for inviting me to give a talk in this big congress. This is really a big congress, and it's my great pleasure to give a talk here. So today I'm going to talk about some simple problem, right? Very simple sort of inequality, and but we see that if this is a simple problem, you see some very deep phenomena. Okay, this stability of sort of inequality. So this is a joint work with Bin-Deng and Li Min-sen, who is here. Yeah. Okay, so the outline of my talk is following. First, I will talk about the stability of surface inequality. We'll talk about two kinds of stability. First is the functional inequality stability. We call it Bianchi-Agnel stability. And second, we'll talk about the critical point stability. This is the main result I'm going to state. And then I will introduce some new stability result for like Caffarelli-Kohn-Nienberg or harmonic mapping inequalities. And finally, I will give the proof for the main result here. Okay, so we start with the simpleness sort of inequality. This is a well-known. This is like a basic, we start PD. This is the basic inequality. And it says that for dimension n greater than 3, so any function u in D12, you have this inequality. Right? So you can control u to the power 2n over n minus 2 by the division norm, and with some constant. Okay, this constant is just depends on the dimension. Okay, this is a well-known sort of inequality. Everyone uses it, and Talenti in 1976 found that all minima. He proved that all minimizer of this can be attained, and they're written in this form, okay, by these functions. So you see that these functions you have are scaling invariants, right? This because this is a scaling invariant, and also you have a translation, right? Because this you can translate this function anywhere, okay? And we call the Talenti bubble. Okay, this is called the Talenti bubble. Now, you can also study the sort of inequality from the functional inequality from the Euler and Lagrange equation. So if you look at this functional, consider this as a functional, you look at the critical point of this functional, the critical points of the sort of inequality, of course, after scaling, because you multiply both sides by constant, it's still a solution. It satisfies this critical point, this nonlinear elliptic equation with a critical exponent, and this is called Yamabe equation. This is a famous Yamabe equation, and for this Euler-Lagrange equation, the classification actually came 10 years later. This by Caffarelli, Gathers, and Spark, and they showed that all possible solutions to this problem, okay, all possible solutions are given by the minimizer, by Talenti bubble. So Talenti bubble is not characterize the minimizer, but also characterize positive critical point. So these are the so from the critical point from the inequality from the minimizer, Talenti bubble are the only solutions. So the question I want to consider today is a Sobolev inequality stable? Okay. So of course you ask in what sense? Okay. What do you mean stability? How do we characterize the stability? So the natural question is from the function inequality. You start from the function inequality. So we know that this is greater equal to 0. So the first stability question is the following. So if we know that the description of this inequality is small, okay? So we know that this is always greater than 0. Now, if this quantity is small, we know that with this quantity equals 0, this is a Tanani bubble. So if this is small, how close is U to the Tanani bubble? So this is and how do we characterize the distance from U to the Tanani bubble? You use the usual the D12 distance. Okay, all right. So you take, because this minimizes they depends on alpha, they depend on the scaling parameter, translation parameter. So you take an infimum of all this, and this is the distance to Tanani bubble. So if this is small, then this should be small. But how to calculate this? How do we quantify this? And this is was the first. This is a proof by Bianchi and Egno in 1993, and they show that there is a constant here. The constant called CBE, the N, the Bianchi-Egno constant, and there's a constant here that this quantity controls the distance to the one. Okay? So this gives you a quantitative estimate how close the stability of this inequality and the distance from U to the Tanani bubble. Okay? And this is a fixed constant. This constant only depends on the dimension. Only depends on dimension. And in fact, recently there are two papers who gave quantitative estimate on this constant. For example, this paper by Dobor, Estefan, Figalli, and denotes. They show that this constant actually depends on n, like 1 over n. So if the dimension is large, this constant gets small. Okay? They have a precise lower bound for this constant. And Cornick recently he proved that actually this constant can be attained. So there is a minimizer to this inequality. So this constant is also attained. Okay. Okay. This is not my what I'm going to consider today. I'm going to consider is the other stability is the stability to the Euler-Lagrange equation. So we consider the stability of Sobolev inequality in the critical point level. So a natural and a more challenging question is to the critical point, the weak solution. So we know that if I have a critical point of a Sobolev functional, then U satisfies the Yamabe equation weakly. So it's a weak solution. Now, once it's a weak solution, then of course you get a strong solution, right? But the usual regularity argument. So the stability question we want to ask, if I know a function is almost a weak solution, if I know this quantity is very small in h minus 1 norm, okay? How close is U to the Tanani bubble? So this is the stability. We know that if this is 0, then this is Tanani bubble. If U is part, and so this is a stability in the critical point level. So if we know this quantity is small in h minus 1, its weak solution is small, how close is U to the Tanani bubble? Okay, and here we assume that U greater than 0, and this is necessary. because if U is not, if you don't assume this, there are many sign changes solutions. So, of course, you have 0 here, and all these are, they are not close to the Tanani bubble. So we have to restrict ourselves to non-negative solutions. Okay. So this is the main question we want to answer today. So if we know the H minus 1, the Yamabe equation, H minus 1 is small. So how close is U to the Tanani bubble? Unfortunately, even for this question, answer is no. Okay, and the easiest example is you take 2 Tanani bubble. You take 2 Tanani bubble and just shift them away. And so if you compute the H minus 1 norm, then this because it's a loss of compactness, right? It goes to infinity. They don't have interaction. The interaction is 0. And so if you take 2 Tanani bubble and just put them far away, and this is in H minus 1 norm is small. But of course, this is not close to any one Tanani bubble. Right? And another situation is the so-called bubble tree. Right? You can also take 2 bubbles, right? One smaller, another larger, and put them together. And these 2 bubbles are, so this will be Z1 equals Z2. And these 2, this bubble tree, this also, in H minus 1 norm is small. So you have these 2 bubbles you take far away, or you take the bubbles in the same place, but arrange different in the different height. And this in H minus 1 norm is small. Okay? H minus 1 norm is small. So in general, if you take a sum of the Tanani bubble, and if the sum of the Tanani bubble satisfies this condition, then the H minus 1 norm is small. Okay? So this is a weak solution. So, of course, then you ask, is this the only possibility? So if we know the H minus 1 is small, this is U close to this Tanani bubbles, sum of Tanani bubbles. And this is the classical result by Struwe, and we call the Struwe's decomposition. And so Struwe proved that if the H minus 1 close to 0, right? If a weak solution and is a approximate solution, then U is close to a sum of the Tanani bubble. So this is the only possibility. Okay. So if the H minus 1 is small, then U close to the sum of this Tanani bubble with these conditions. So this is called the Struwe decomposition. So what I want to discuss today, can we quantify Struwe decomposition? Can we quantify Struwe decomposition? So first, let us introduce some notations. So we take the sum of a Tanani bubble, and this we call this a manifold T. So you take many Tanani bubbles, and this form a manifold. We call this a manifold T. And so the distance from U to T is this inf to this manifold. Okay? So I call the gamma U the H minus 1, the H minus 1 of the nonlinear, okay, equation, the H minus 1 norm. So what is, yeah. Okay, this is a very good question. So what the Struwe theorem says, if you know your energy, so actually if your energy is bounded, then you can show there is a number. This number depends on your sequence. So this number actually is fixed according to your sequence. Yeah. And this sequence is called the Pierce sequence, Panhard-Simons sequence. Yeah. So, so the Struwe decomposition mathematically, we can state in this way: if the gamma u, so h minus norm goes to 0, then the distance from u to the Talenti, to the manifold Talenti bubble goes to 0. Okay, so this is Struwe's decomposition. Or in other way, the distance from u to the Talenti bubble is little O1 in terms of gamma u. Right? So this is the Struwe decomposition. So of course, we are not satisfied with this little o. We want to know what exactly is this little o. Okay, what is this little o? So we want to ask a more quantitative question. So can we show that this distance from Talenti bubble, manifold Talenti bubble, less equal to gamma u? Or we can have some quantitative control. Okay? We want to understand what is this little o here. And so for the one bubble case, Ciraolo and Figalli and Maggi in 2018, they showed precisely the linear relation. So distance from u to the Talenti bubble can be bounded by gamma u, by the h minus 1 norm. Okay? And what about the mu greater than 1? So you have 2 or 3 bubbles, more bubbles. Okay? And so Figalli and Glaudo in 2020, they show that for lower dimensions, dimensions 3 and 4 and 5, and for any integer mu, okay, you still have this linear control. So in dimension 3, 4, 5, and for any number of bubbles, you still have this linear control. So this is linear. Yeah, this constant only depends on n and mu. Only depends on n and mu. Yeah. So I should say, when I say this, means there's a constant, and this constant only generic constant depend on n and mu, and number of bubbles. Yeah. So this strange condition, this dimension. So of course, naturally you ask what happens when dimension 6 or higher, and they show that when dimension greater equal to 6, you don't have linear control. They construct counterexamples showing that actually this is greater equal to, much greater than gamma u. Okay? And so they conjectured, based on the example, they conjectured that in dimension 6, you still have almost a linear control, but you lose a log. So there's a log gamma u here. And in dimension 7 or higher, they conjecture that this is gamma to some power. But this power should be less than 1, should not be linear, should be some sublinear. Okay? But they don't know this, the precise value, this power alpha. Okay? And this is our main result. This is joint work with Deng and Sen, and we appear in Duke. So we gave a precise the relation between this u to t and gamma u. So in dimension 6, we have gamma u times square root of log gamma. Not so in the original conjecture is log gamma, but it should be square root of log gamma. And for dimension n greater to 7 is n plus 2 gamma to the n plus 2 over 2 times n minus 1. And this is less than 1. Okay? This is so this is some sublinear growth. In fact, we also show that this is the best possible. So you have an example that show that this is greater than this. So I should say greater, not this great, not double greater, just greater. So in other words, all these are optimal. Okay, these relations are optimal. And of course, the C depends on N and mu. Only depends on the generic constant. Doesn't depend on U. So this is the result give a quantitative estimate of the Struwe decomposition, and it shows that in high dimension, the Struwe decomposition, the distance from U to Talenti bubble manifolds is with the H minus norm is a nonlinear relation, and in lower dimension is a linear relation. Okay, so let me give a summary. We start with the Sobolev inequality, and we discuss two kinds of inequalities. First one is the function inequality, and this is Bianchi and Agnew. We have this inequality, and the second stability is stability from the critical points, and here we have linear relation in lower dimension and nonlinear relation in high dimension. So this is the main result I'm going to present, and I will show you the difference between lower dimension and high dimension and how we get this this exponent. Okay. Before this, let me just mention that some new results, some later. So we discussed the Sobolev inequality for exponent 2, which is the Hilbert case, P. But in general, when depend P greater than 1, you also have a Sobolev inequality. But this course, this is quite nonlinear. Right? And the exponent is NP over M minus P. And again, the minimizer is attained by Talenti bubble. You have a similar Talenti bubble. And so you can ask the same question. What about the stability of this inequality for P between 1 and n? And it turns out for P equal 2, it's easy because it's, you can use Hilbert norm and inner product. But for P not equal to 2, then the proof is quite nonlinear. The proof is very take 3 papers, Figalli and Nomaya, and finally Figalli and Zhang, and they showed that for P greater than 1 and n, you have this optimal estimate, and this is optimal. And the proof actually is they use optimal transport. So you use not a classical PD. This is optimal transport proof. This is a proof. And of course, an open question is stability in the critical point level, which is completely open. We have no idea, even for one bubble case. We don't know how to prove in the critical point. This is a proof. Which this is the last one. Oh, this is in the entire domain. Yeah, this is in the entire domain. So for Pico 2, right, you see that this is the Bianchi agonal. So this problem actually is coming from geometry, because when P is 1, we know the Sobolev inequality becomes isoparmetric inequality. Okay? So This is a geometric inequality. This says for any set with a suitable family of set, you have this the area can be bounded by the volume can be bounded by area or so by the parameter. And we know that all minimizers for this problem are balls. This is the same as the Talenti's hyper result. And so for this problem, you can ask, what about the stability of this isoparammetric inequality? In fact, this kind of question was first looked at when Pico won. Okay, to look at the stability of the isoparammetric inequality. So you look at you rescale this, right? You scale this constant. This constant is achieved by a ball. So you achieve this constant, and so you ask if this quantity is close to 1, how close is a set close to the ball? Right? So this is analog to the Bianchi-Eganos result. And the closeness, the closeness can be controlled by this distance from this set and to any ball. So this is how you measure from distance from E to any ball. So you look at this the difference, right? And divided by the volume, and this number E, and so this quantity can be controlled by this quantity. And this is proved by Fusco and Maggi and Aubin-Talenti, and Figalli and Maggi and Aubin-Talenti. And these are two different proofs. This proof, the second proof is optimal transport proof, and this is called a Hall's conjecture. So in fact, this is the first look at Pico 1 case. This is the isoparammetric inequality. Now you can also ask the same question about from the isoparammetric inequality from the critical point level. The critical point of the isoparammetric inequality is the same surface. It's the mean curvature equals constant. So you can ask the same question, conservation of the critical points, right, for this isoparammetric inequality. And this has been already proved by Alessandro. Right? If we assume the surface is embedded, then the ball is the only solution for this critical point. Right? And if you don't assume the embeddedness, if you only immerse, then you have Ventis example, which is correspond to the sign change solution for the Yamabe problem. So you can ask the same thing. What if is approximately same surface? Okay, in the critical point, if it's approximately same surface, how close is this set E to the union of balls? And Butcher in 2011, he constructed this weakly interacting Talenti bubble. He showed that you can put many balls together, and the L2 norm is small. In the critical point level. Okay? And Dagadino, Maggi, and Mihai, and Neumeier, they show that they prove the analog of a Struwe decomposition. So if the L2 oscillation is small, then E is close to the union of balls. So this is like the Struwe decomposition for the isoparammetric inequality. Okay. And of course, you ask the same thing about stability in critical point level, and so this is the natural quantity. One should ask what if this L2 is small, or if so this is like H minus 1, L2 small. How close is E to the union of balls, right? To the union of balls, and unfortunately, you don't have we don't have a full picture of this yet. The best result by Ciraolo and Maggi in 2017, and they show that if you replace this L2, L2 is the natural space in this for this problem, but instead of L2, you replace L2 by L infinity. They found some alpha so that this can be controlled by this power to the alpha, but the precise value of this alpha is not explicit. It's only some alpha. Okay. So for Pico 1, this is also this is still open. This is a geometrical problem. Yeah. I would discuss some further different for this stability question. Another interesting inequality is Carpenter-Koenig-Nielberg. This Carpenter-Koenig-Nielberg has been used in Navier-Stokes. Like you use this for energy estimate. You also use this Carpenter-Koenig-Nielberg inequality. And this one has some new feature for this problem. This is unlike the Sobolev. For the Sobolev, you get a stability, and you also get non-degenerate stability. But for the Carpenter-Koenig-Nielberg, sometimes you get degenerate stability. Okay, so let me show what I mean the degenerate stability. So here, Carpenter-Koenig-Nielberg is I have two constant A and B, and the Carpenter-Koenig-Nielberg is somehow is an interpolation between the hardness inequality and the Sobolev. So if both A and B equals 0, this becomes Sobolev, and if A equals 0, B becomes 1, this becomes Hardy. So we know that for Hardy is never attained, and Sobolev is attained. So there is a bottom line, right? A curve bottom somewhere where above this is attained, below this is not attained. So this is the critical. This is the Boyle and Lagrange equation. In fact, Katrina and Wang found precisely the curve in which this is attained and this is not attained. Okay? Now, for the classification of the extreme solution, the so-called Figalli and Schneider curve. And so fixed at A, you have this B, this function which depends on A. And so Dobot and Esteban laws, they show that if above the Figalli-Schneider curve, actually B greater equal to this, all extreme solutions are radially symmetric, and they're classified like this, and including the Figalli, the B equals the on the curve, including when B equals the BFSA. And the stability of this question, this Carpenter-Koenig-Nielberg inequality, I discussed with Wu, and we showed so if B is strictly above the Figalli-Schneider curve, you have the same functional inequality, you have the same stability in the critical point level, and you have almost get the same type of result. You can also show that this is at 10. Now, when B equals the Figalli-Schneider curve, then there's something interesting phenomena come, and this is a very recent work by Robert Frank and his student. They show that actually you have a degenerate stability. You don't get a score because at this place, the solution bifurcate. You have bifurcation. You have a degeneracy. And so you control this quantity, you don't control score. you control to the fourth order. So this is a degenerate stability when B equals on the Figalli curve. Now, in terms of critical point, you see this is strange phenomenon, strange exponent, 1 over 3 and minimum 1 over 3 and the P over 4. And since, for example, when P is large, you see that this distance is controlled by P over 4, not in the Sobolev case is P over 2. So here is a P over 4. So you have a degenerate stability here. Right? So all this, this is some new phenomena for the carbonic network. So above the Figalli curve, you have everything similar to the Sobolev, but on the Figalli curve, you have degenerate stability. You have some higher order exponent here, high order exponent. I want to discuss another one which is quite interesting is the harmonic map. Here we see instability, not stability, but instability. And this is also quite surprising for us. If you look at the harmonic map from R2 to S2, so this division norm, we can define the degree. And so by classical with the Wood and the Lamar, we know that this division norm controls the degree by 4 pi. This is and equality holds only if this is a harmonic map. So, and all the harmonic map can be classified. So this is a harmonic map, stationary harmonic map. And this harmonic map, they're all given by stereographic projection of meromorphic functions. Okay, this can be completely classified. And so if we give a degree, the harmonic maps are stereographic projection of P over Q, and where P and Q, the maximum degree is the D. And D is your degree. Okay? D is the degree. So the dimension of the harmonic maps of a degree D is 4D plus 2. So for example, degree 1, you have 6 dimensions, 6 parameters, and dimension 2, you have 10 parameters. So you have 10-dimensional manifold for degree 2. Degree 1, you have a 6-dimensional manifold. Okay? So we answer the same question. Actually, we did not answer first. Somebody else answered first. So if this quantity is small, can this quantity control the distance from U to the harmonic map? Because we know when this is 0, U equals the harmonic map. So if this is small, can we control U to the harmonic maps? And so this is a similar type of, we'll ask the similar type of Bianchi-Agnel stability for harmonic maps. Do we have this kind of inequalities? Okay? And the answer is yes in degree 1. And this is proved by Bernard Mattel and Muratov and Simon in 2021. And they showed precisely the statement. So if degree is 1, we have precise control to the distance to the degree 1. Okay? And so this for degree 1, we have the stability, complete stability. Right? And recently there are also 2 other proofs, simplified proofs. This proof is very long, and it's also taught by harmonic map flow. These are shorter proofs. So we ask, what about degree 2? Can we have the same kind of stability for degree 2? For degree 2, and unfortunately, the answer is no. So we show that for degree 2, you can, for any large number, m, you can always find a number, find a function u with degree 2, so that the distance from u to the degree 2 harmonic maps is greater than or equal to m times this. So which means this term cannot control this term. Cannot control this, just a simple this term. So this means there is something, you cannot have a linear control. There should be some kind of a nonlinear control. Right? And we conjectured this is the nonlinear control. Based on our example, we have this our example, and we conjecture that actually there should be a log correction for the control for degree 2 or higher. So when d greater than 2, this should be not, this controls, this should be the distance, this times the log controls there. This problem is quite difficult because the manifold, the dimension of the manifold degree d harmonic maps is 4d plus 2. So for example, when d is 2, this is already 10-dimensional manifold. So you have 10 parameters there, okay, fighting each other. And so there are some partial results by Rufflin in last year. He almost proved this conjecture, but not precise this conjecture. And so he showed that you can decompose into some degree, small degree maps, and so then this u to this small degree maps is controlled by this, and so he did not completely solve the conjecture, but suggests that this conjecture is true. And also for the half harmonic map, you can do the same kind of proof. In fact, for steady state half harmonic map, this is given by the finite Blaska product. This proof by the non-degenerate proof by Yannick and myself and Zin, and also Nesman and Ciraolo. And we also prove a similar result. For degree 1, you have stability. In fact, for degree 1, we have the precise constant. Right? We have the explicit constant. For a high degree, you don't have a stability. You lose the stability. So, in the remaining time, I will discuss how we prove. I go back to the Sobolev inequality, and let me give you the idea of the proof of the quantitative estimate of the Struwe decomposition. So I want to show you why the dimension is, why there's a departure of the estimate from dimension 5 to 6, and why we get this nonlinear, and how we prove this nonlinear estimate. So let's call it P is n plus 2 over minus 2. It's a 2 star minus 1. And so let me now go over Figalli and Glaudo's proof for lower dimensions, and I will show you where they stuck and how we fix the proof. So you start with a sequence of solutions with the weak norm is very small. So you write as a Laplace u plus u to the power p equals f, and the h minus 1 norm is small. Okay? And by Struwe decomposition, you can decompose u as sum of the Talenti bubble plus a small term. Okay, and in fact, in the Figalli Glaudo, they also rescale. They also put a scaling parameter here, but actually you don't need this scaling parameter. So this rule is orthogonal to all these kernels, okay, to all this. And so the rule satisfies this problem with right-hand side, which is h minus 1, when you use the weak. Okay, so what do you do? And so the idea, you multiply both sides by some test function and try to get an estimate. So what the first test function you can think of is rho itself, right? Rho itself is in D12. So you multiply both sides by rho. And for the right-hand side, f times rho, okay, you can just use holder. You can, because you only know f is h minus 1. So, okay, this is the only thing you can do, okay, the right-hand side. On left-hand side, the leading term on the left-hand side, if rho is 0, then you have the sum of the Talenti bubble minus the summation of the u to the power p. So this is the error from the Talenti bubbles. Okay, so you have this is the error from the Talenti bubble. Okay, you do same kind of holder. So this can be controlled by the interaction of the bubbles, right? Okay, this is and for this because you know rho is in L2, gradient L2 D12. So you can increase this to L to the 2 star norm, and then the remaining term here will be L to the 2 star prime. Okay, and for n less than 5. And u to the p minus 1 or uj, L to the 2 star prime is like u to the I p times uj, which is the interactions. And so you have, and of course, because rho is orthogonal to all the kernels, so you have coercive. So you have the L2 norm, the diffusion norm is bounded by this is F, right? This is the weak norm h minus 1, and times this, and times this the interaction term. So, but unfortunately, when dimension is greater than 6, this breaks down. When greater than 6, this norm will compute. Just you put 2 bubbles and just compute. You found this norm behaves like interaction times a log. There's a log to this power, 2/3. And for n greater than 7, is a sublinear of the interaction. It's p minus 1. Okay? And so which is much bigger than the interaction term. So now, if you can write this as an interaction term, then the rest just by energy estimate. It's just then you can have an estimate of the interaction in terms of the h minus 1 norm, and then you go back, you get the diffusion norm, the L2, the diffusion norm in terms of the h minus 1 norm, and then everything is linear. So as long as you can show the interaction can be bounded by h minus 1, then the energy estimate kicks in, you get the linear control. Now, the problem for n greater than 6, this no longer works. So this is no longer an interaction. Okay, it's much bigger. This term is much bigger than the interaction, because we do this term is much bigger than the interaction. So this term is much bigger than the interaction, and so you cannot do the energy estimate. So what is our idea? So our idea is to find the best approximation of the solution. And obtain the precise point-wise estimate. We need a point-wise, the rule. You cannot just simply use the holder to, you have to find out the precise point-wise estimate for the rule, okay? So what is the best approximation? So if you suppose you are close to the Tanani bubble, you're very close to the Tanani bubble, the sum of the Tanani bubble. And so what would be, you take the sum of the Tanani bubble. Okay, take the sum of the Tanani bubble. And we know that the sum of Tanani bubble is, if you compute the h-1 norm, is very small. Okay, it's very small. But we need to know precise how small the sum, the next order. Okay, so if you take the difference, so difference is given by this, and we need to find what is the best estimate approximation for rho. Okay? And it turns out the best approximation for rho. So what is the best right-hand side for the sum of Tanani bubble? For the sum of Tanani bubble, the best right-hand side are the Lagrange multiplier. Okay? And the reason is that if you take the summation of the Tanani bubble, and you can always find some phi zero, so that the sum of Tanani bubble almost solves the Yamabe problem up to Lagrange multiplier. Okay, and this Lagrange multiplier is the best approximation you can find. So you use this right-hand side, and you solve this problem. You find this phi zero, and this phi zero, you have this point-wise estimate for this phi zero. Now, after you get this, then you return to Figalli and Glaudo's process. Yeah. Once you have this point-wise estimate, you go back to the process and you can compute. You found the best exponent. So this is the key idea. The key idea is to find the best approximation. The best approximation should be this. This should be rho zero. Okay. So what is the best approximation? What is rho zero? Okay. If I give a sum of Tanani bubble, what is rho zero? Okay. And we found this estimate for rho zero, which is if you're close to each of the bubble, you have r to the 2 minus n, and away from the bubble is r to the minus 4. And you have this point-wise estimate. So using this point-wise estimate, and you go back to the Figalli's procedure, and you found the exponent. So, and of course, the existence is very easy. Okay, this is just finite dimension reduction. This is a very simple reduction method. The problem is you want to estimate get the point-wise estimate. Now you may say, okay, looks like this statement is very easy, right? But the problem is we don't want to impose any condition on the bubble. We have no idea the bubble, it's just a symptom of a Tanani bubble. So this estimate should hold for any Tanani bubble, okay? For any Tanani bubble. So what is the difficulty here? Okay, so the difficulty is in all the previous work, Either all the bubbles, the clusters, they're the same size. With the existence, the bubbles are the same size. Or you have a bubble tau. Okay? But in the general case, because I only know it's a Talenti bubble, so in the general case, you can have a bubble tower. Inside the bubble tower, you may have a bubble cluster. Inside the bubble cluster, you can have bubble tower. And all this bubble tower, bubble cluster, they're all mixed together. So with those construction, you can assume it's a bubble tower, you can assume it's a bubble cluster. But in the general case, in the general case, this is a bubble tower, but maybe underneath this bubble tower, you have a bubble cluster, right? This is a bubble cluster, but underneath you may have a bubble tower. And all this you have a mixed bubble tower and a bubble cluster. And our pointwise estimate does not depend on any of the situation. That's the main problem. We need to make sure you have a pointwise estimate which works for all situations. Okay. So there's also a parabolic. So how do we get this pointwise estimate? So we to obtain RPL estimate in all these situations, we use contradiction argument. And for each bubble, we decompose into 3 regions, inner and leg and the exterior. And so each bubble you have 3 regimes, inner and leg and the exterior. But different bubbles, these regions may overlap. Okay, different bubble. So for example, if this is a big bubble here, right, and the core region is here, the inner part is here. But inside this inner part, you will see another bubble, right, with a core and with a leg and with the outer. So all this, and sometimes these regions can overlap, right? These 2 leg regions can overlap, the core regions can overlap, and all this, you have all these situations, okay? So the basic idea, the strategy of the proof, of course, the proof is very complicated, right? So in the core regime, you use a standard Bloch argument, right? And you use also organicity. And in the exterior, far from the core of all bubbles, you use a pointwise estimate, use the Green's representation. And the major difficulty is the neck region. So if in between the bubbles, in the neck region, because the neck region may go to infinity. The neck region may be very narrow, but may go to infinity. And so the main factor we use, the fact is the neck region, even though it may be unbounded, okay, but it's a narrow domain. And for narrow domain, we can still use the maximum principle. And we can construct suitable solution for these narrow domains. Since my time is up, I think the next I have another 10 slides for the proof, but I don't want to bother you. So in the summary, what we prove is stability of solving inequality. In the critical level, we see a nonlinear stability for the Struwe decomposition. And the proof, we use pointwise estimate, and which gives us estimate in all situations in the sum of Talenti bubbles. Okay, thank you.
Thank you, Professor Wei, for the very clear introduction to the subject matter. So maybe I start with the question session with asking, have you explored the dynamical consequence of your estimates? Because it seems that it has some natural connection if you, for example, run dynamics.
Oh, actually, I did not show this. We use this idea for this paper. Oh, sorry. For the Fujita equation. So, for example, in this Fujita, For this Fujita equation, we show that there's no type 2 blob, all blobs are type 1. And here you have to see the dynamics of the Talenti bubble, because we don't put any assumption on the solution. So you have all these Talenti bubbles, and they have a dynamics. We have to estimate the dynamics, and this is more difficult. This is close to 200 pages. This paper, very long. So we'll see the dynamics of the sum of Talenti bubbles. Yeah.
Okay. Thanks, Professor. And any other question from the audience?
We show that asymptotically you have a dynamic law for all these parameters, and then there's no type 2 blob. All blob must be type 1. Yeah. Hi. Twisted. Oh.
Okay. I would like to ask, can you explain more about how you use the optimality of group zero? Like you take it to be the.
We know U is close to the Talenti bubble, right? Some of the Talenti bubble, but you want to say what is the best approximation for U. So you write U as a sum of Talenti bubble plus rho. It turns out the best approximation for rho is this equation. Rho, the best approximation that gives you the optimal result is this rho 0. Yes. So this is like this is another critical point in rho. It's like you have a critical point in rho. But because rho is orthogonal to all these kernels, that's why you get this Lagrange multiplier. Yeah. Yeah.
Thanks. Maybe one more quick question.
For the harmonic map, the instability, if you know that there is no bubbling, that is, you have L2 close to a degree D map, because this is very different from the Talenti situation.
You cannot use L2.
Yeah, but you have stability then. That is, if there is no bubbling, that
No
is, if you are close to in weak norm.
Yeah.
If you are L2 close, say, degree D map.
Then you have, you have a
So the
stability.
instability is only coming from the negligence.
Yeah. Exactly.
Exactly. Way to keep that into consideration, in a sense, I don't know.
Okay. This is a very good, like the Sobolev map, Sobolev inequality. Where do we get the optimal? The optimal is not because of the core region or the outer region. The optimal is at hand, precisely is the neck part. The neck part contributes to the optimal. And the same thing for the degree 2 harmonic map. The neck region gives you the instability. Yes. Yeah.
Okay, because they interact too much. The bubbles interact too much in comparison to Yamabe.
Yeah. They interact too much in the neck region. Yeah.
Thank you, Professor Wei, for the answering all these questions. And let's give another round of applause for the speakers. Okay, so I think it's time to wrap up the morning session in this room.